In this lesson, we want to review relations and functions. So I know most of you took Algebra 1 and Algebra 2 before joining this course, and essentially you already know what a relation is and what a function is, right? You have those concepts down. So this is basically a review for you, but it never hurts because functions are something that are so important and used throughout the study of algebra and all your higher level math courses. So our review is not something that's going to really kill you, right? You want to make sure you really understand this topic. So we'll talk about functions here, and then over the course of the next few lessons, we'll talk about function notation, we'll talk about domain and range, and we'll talk about using the vertical line test. All right, so let's start out with the basic definition of a relation, and then we'll kind of move into functions. So a relation is any set of ordered pairs. Now, before I kind of move on from this, let's think about what an ordered pair is used for. Normally, we see ordered pairs when we work with equations with two variables involved, normally x and y. So something simple like x plus y equals 3. I can display the solutions for this equation using ordered pairs, right? Let's say x was 0. I would have y equals 3, right? So an x value of 0 and a y value of 3, those guys are related to each other because they represent a solution to this equation. So I could write this as an ordered pair, 0, 3, right? An x value of 0 is related to a y value of 3. That, again, solves this equation. I could also do an x value of 1 and a y value of 2. So I could have an x value of 1 and a y value of 2, right? So on and so forth. I could do 2, 1, right, if I wanted to. An x value of 2 and a y value of 1. Now, there's an infinite number of ordered pairs as solutions for this equation, so I'm not going to continue further beyond this point. But I want you to understand that ordered pairs are really just a nice way to write two pieces of associated information or two pieces of related information. Here, the x and the y values are associated with each other because they represent two values that when plugged in for this equation are going to give us a true statement, right? They're solutions for the equation. But we could also have some kind of random information. Let's say we had set A here, and set A just contained these kind of four random ordered pairs, okay? So I have 3, 5, 9, 6, 1, 3, and 8, 7. So we don't know the association between these numbers. We're not given any type of equation or any type of like back information on this, but this is something you'll see in this section pretty often, just so you can get the concept down of what a relation is. Again, it's just a set of ordered pairs. Something like set B, again, this is equal to, we have 3 ordered pairs here, 1, -4, 6, -7, and -4, 4. Now, ordered pairs don't have to just relate kind of numerical information. It doesn't have to be solutions for equations, or it can really be any two pieces of related information kind of put together nicely, okay? So for C here, what we have is numerical grades and then associated letter grades. So a grade of 38, if you get that on a test, you get an F, right? So 38 is associated with a letter grade of F, or it's related to a letter grade of F. 73 with a D, 81 with a C, 95 with an A. Then something like set D, let's say we related kind of people in a group and their pets. So let's say John has a cat, Mary has a dog, James has a bird, Lacey has a hamster. So in each case, the ordered pair is just giving us two pieces of related information. It's wrapped inside of parentheses, it's separated by a comma. So whenever we have a set of ordered pairs, we have a relation. All right, so let's look at a kind of real world situation. We'll set up a little equation. We'll go through some of the kind of vocabulary that's going to be involved in this section. So we have here that Heather purchases gas from the local station for $5 per gallon, which includes all taxes and fees. So $5 per gallon, okay? So let's set up a little equation, and we're going to use x and y. And I've already kind of pre-written this stuff for us. So we're going to let x equal the amount of gas in gallons that she's going to choose to purchase. And then y is going to equal the total dollar amount of her purchase. So the equation we end up setting up is y, again, this is the total dollar amount of her purchase, is equal to or the same as 5, the cost per gallon of gas, times x, the amount of gas in gallons she's going to buy, okay? And you can think about this if I plugged in a 1 here. Well, it's $5 per gallon. She buys 1 gallon. This guy's going to be 5, right? If I plugged in a 2 here, she buys 2 gallons of gas and multiply it by 5, the cost per gallon, I get a y value of 10, so on and so forth. Now, there's a couple of things that I have related to this. First, I've said that y is the dependent variable, and I've said that x is the independent variable. What do those two terms mean? Y is the dependent variable because it depends on her choice of x, right? The independent variable. Okay, so the independent variable is something she chooses. The dependent variable is something that comes as a result of her choice. She chooses how much gas to buy, right? She rolls up to the station and she chooses to buy what? She chooses to buy no gas. She gets upset at the price and says, I can't afford it or I don't like it or whatever. She leaves. She doesn't buy anything. Okay, so she chooses in that case to buy 0 gallons. She pays $0. Okay, if she rolls up to the station and buys 1 gallon, she pays $5, right? I multiply 1 times 5, I get 5. Again, I showed you that already. So again, the independent variable here is X. It's something she chooses. And Y is the dependent variable. It's something that is a result of her choice, okay? Now, we also have other names for the independent and dependent variables. For the independent variable, we call it an input. It's something we're going to plug in. So in this case, again, let's just say she buys 3 gallons of gas. That's my input. Okay, in this case, it's 3. And my output is another name for the dependent variable. So I plug in a 3, that's my input. I multiply it by 5, and then I get 15 as an output. So we would say this is 15, or this is my output. Okay, so you'll hear that a lot in this section. Now, in this particular case, I gave you something known as a domain restriction. We're going to talk about domain and range very shortly. I know most of you already know what a domain is, but again, we'll cover it in a second. I said that X here, the independent variable, has to be greater than or equal to 0. So I put that in there in this particular case because she can't go on and buy a negative amount of gas. Okay, when you describe a real world situation, you have to think about these things. If she rolls up to the pump and she decides not to buy anything, that's fine. She could buy 0 gallons. She can buy some positive amount up to the point to where her car is full or the station has no more gas, right? Those are the kind of constraints in the real world. But she can't roll up to the station and pump a negative amount of gas, right? She can't siphon gas out or something silly like that. So we put this constraint in here to say that X, the amount of gas in gallons she's going to buy, is going to be greater than or equal to 0. In this example here, I'm going to further constrain X, and I'm going to say that X is going to be greater than or equal to 0 and less than or equal to 5, and X is an integer, okay? So that means she could roll up to the pump and buy no gas, 1 gallon, 2, 3, 4, 5 gallons of gas. Those are her only choices, okay? Just to make it nice and easy so we can end up with a set of these ordered pairs. So we have 0, 0, 1, 5, 2, 10, 3, 15, 4, 20, and 5, 25, right? Each of these represent solutions to this equation. Again, given these two constraints, these are the only possibilities, okay? And you can see that these values are related to each other. Buying 0 gallons of gas is related to spending $0. Choosing to buy 1 gallon of gas is related to spending $5, right? So on and so forth. Now, a cool way to look at this is with a little table. A lot of times you'll kind of set this up with real world information. So if we have gallons of gas here is X, amount paid is Y, and again, our ordered pair, X, Y. So we have 0 gallons of gas means she pays 0, 0, 0, right? Going all the way through this, again, if she bought 5 gallons of gas, she pays $25 total. It's 5, 25 as an ordered pair. Now we're going to revisit that example in just a second so I can give you a definition of a function. But before we do that, I want you to understand what the domain and range represent when we're talking about a relation or a function, okay? So the domain is the set of allowable values for X, and the range is the set of allowable or possible values for Y. So previously, when we talked about domain in this course, it's been things that have been restricted, right? Dividing by 0. If you had X in the denominator, you couldn't put an X value of 0 there because division by 0 was undefined. So as an example here, we have Y equals 2X, and I think about what's possible for X. Is there anything that would restrict me from plugging in something for X? The answer to that is no, right? I can plug in anything for X and multiply it by 2. So the domain here would be all real numbers. And because I can plug in anything I want for X, I can make Y as small or as large as I want. So for the domain, I could say that it's all real numbers, and I could write it out like this, okay? But that's a little bit lengthy, and I don't really like to do that. So I'm just going to use interval notation, and I'm going to say this is from negative infinity to positive infinity because it just includes all real numbers. And then for the range, it's going to be the same thing for this guy. So from negative infinity to positive infinity. All right, let's think about this guy right here. So we have Y equals the square root of X minus 1. So what would my restriction be here? Think about the fact that you cannot, in the real number system, take the square root of a negative number. Okay, that's not allowed. You can do it with the complex number system, but if we're working in the real number system, which we're doing right now, we're not going to be allowed to take the square root of a negative number. So what I would have to do is I would have to take this radicand here, this x minus 1, and I would have to say this needs to be greater than or equal to 0. Okay? I would add 1 to both sides of this inequality. And so for my domain, I would basically say that it needs to be greater than or equal to 1. Okay? So it could be 1, that could be included. And then anything out to positive infinity, right? So if I plugged in a 1 there, I'm okay. 1 minus 1 is 0. I can take square root of 0, that's fine, it's just 0. And then I can take the square root of any positive number. So if I plugged in a 2, right? 2 minus 1 is 1, square root of 1 is 1, I'm fine. But if I plugged in something like, let's say 0, 0 minus 1 is negative 1, square root of negative 1, again, in the real number system, that's not possible, okay? So let's erase this and this. So my domain basically is from 1, including 1, out to positive infinity. Real quick as a side note, you might see this in your course. You might see them write it this way. So they might say something like the set of all x such that x is greater than or equal to 1. Now, this is set builder notation, okay? And all this means is that x is a real number, and this vertical bar means such that the x that we said was a real number has to be greater than or equal to the number 1. Okay, so it's just giving you the conditions. The set of all x such that x is greater than or equal to 1. Okay, so that's set builder notation. I'm not going to use it here, but you might see it in your book. So now let's think about the range. So what is the range? So if we think about this carefully, again, the smallest value I can plug in for x is going to be a 1. If I plug that in, 1 minus 1 is 0. Square root of 0 is 0. So the range would start at 0. That's the smallest it can be. And then it can be any positive number out to positive infinity. So from 0, including 0, out to positive infinity. Okay, so we'll go more into depth on domain and range in the next lesson. We'll go way more into depth on it actually. But for right now, this is just kind of the basic idea of domain and range. The domain is the set of allowable values for x, or basically all your x values. The range is the allowable values for y, or all the y values for that relation or that function. All right, so kind of revisiting these ordered pairs that came from our y equals 5x. If I asked you for the domain and range for this example, all you would do for the domain is find the x values for the ordered pairs you have. So the domain is just basically what? It's each first component. So each first entry, so the leftmost entry of each x value. So I'm highlighting all of those now. So 0, 1, 2, 3, 4, 5. So that's your domain, right? This set would be 0, 1, 2, 3, 4, and then 5. Okay, so that's the domain. And then the range is very simple also. It's just the kind of y values that are involved here. So 0, 5, 10, 15, 20, and 25. So for the range, we have 0, 5, 10, 15, 20, and 25. Okay, so that's your range. All right, so now that we understand the concept of domain and range, let's talk about the definition of a function. So this is something you really want to pay attention to. And there's several different definitions that kind of go with this. So I'll read a few of them and you just take the one that you like. So essentially, a function is a special type of relation where each x value or member of the domain is associated with only one y value or member of the range. Okay, so all functions are relations, but not all relations are functions. Now let me read you a few alternative definitions you may hear. So a function is a relation in which for each value of the first component of the ordered pairs, there's exactly one value of the second component. Another definition, a function is a set of ordered pairs in which no first component is repeated. So you'll see this in these examples here. If you have a duplicate first component or a duplicate x value, you're not going to have a function. Then you might also hear a function is a rule or a correspondence, okay, that assigns exactly one range value, that's a y value, to each domain value. Again, that's an x value. The definition that I like the most, the definition that always stuck with me is for each x, there's one y. Okay, that's as simple as it can get. For each x, there's one y. So for each x or member of the domain, there's one y or member of the range that's going to be associated with it. So what I did was I took the kind of ordered pairs we were working with from the y equals 5x, and basically I set up a mapping diagram. So we're showing the association between the members of the domain and the members of the range, and this is very common to see this in this section of your textbook. So an x value of 0 is corresponding to or linked up with or associated with a y value of 0. An x value of 1 is associated with a y value of 5. An x value of 2 is associated with a y value of 10. X value of 3 is associated with a Y value of 15, an X value of 4 is associated with a Y value of 20, and then an X value of 5 is associated with a Y value of 25. So this relation, this set of ordered pairs, represents a function because for each X value or member of the domain, there's exactly one Y value or member of the range that it's associated with. So this guy is a function. All right, so let's go through and just look at a few examples. And then again, as we move on throughout the next few lessons, we'll start working with this in the format of an equation. It'll be a little bit more challenging, but we'll get through it. So here we have f, and f is again just a set of ordered pairs. So we have 2, 6, 9, 1, 2, 13, and 8, 7. Is this a function? Remember one of the definitions I read to you, you basically find out if you have a duplicate x value, you don't have a function, right? Here you have a 2, and here you have a 2. Well, what's the problem? 2 is associated with 6, and then 2 is associated with 13. And you can see that very clearly in the mapping diagram. An x value of 2 is associated with or linked up with a y value of 6, and also a y value of 13. So there is no clear association here. If I said, hey, if x is 2, what's y? Your answer could be 6 or it could be 13. You don't know what to answer. For a function, essentially, if I give you a value for x, if I give you an input, you have to be able to give me a very specific output, right? Or a value for y or a value from the range. So for 2, again, it's associated with 6 and also 13, so this is not a function, right? The fact that 9 is associated with 1 and 8 is associated with 7, those are fine. It doesn't violate the definition. But because this fails, the whole thing fails. So we would say this is not a function. Let's look at another one. So we have g here, and it equals, again, just a set of ordered pairs, 1, 4, -7, 3, 2, 5, and 8, 6. So any duplicate x values? No. Right? So you can say that you have a function here. An x value of 1 is associated with a y value of 4. An x value of -7 is associated with a y value of 3. An x value of 2 is associated with a y value of 5. And an x value of 8 is associated with a y value of 6. So for each x, there's one y value that's associated with it. So this is a function. All right, let's take a look at another one. This one I'm going to tell you in advance is a little bit tricky. So we have h is equal to, again, we have a set of ordered pairs. So -2, -1, 3, 4, 6, -1, and 9, 8. Okay, so some of you would immediately say, okay, you have a duplicate y value here of -1, not a function. But you'd be wrong if you said that. We say that for each x value, it's associated with or linked up with or corresponds to one y value. If I said, hey, what is y when x is -2? There's a clear answer. It's -1. What is y when x equals 6? There's a clear answer. It's -1. It doesn't matter that these two x values are linked up to one single y value. That's all right. It doesn't violate the definition of a function, right? The problem comes when one x is linked up to more than one y, but two different x values, or you could say two or more x values, could be linked up to the same y, right? That's fine. So for each x here, there is one y value that's associated with it. -2 is associated with -1, 6 is associated with -1, 3 is associated with 4, 9 is associated with 8. So this is a function. Let's look at two examples with some non-numerical information. You'll get these also. So what this set is representing, this guy f, it's going to represent takeoff cities, so you're kind of flying somewhere, and destination cities, okay? So the first guy is where you're taking off from. The second guy is where you're kind of landing or your destination. So you have New York, Miami. You have Boise, San Diego, Baton Rouge, Orlando, and Denver, Dallas. So again, I'm just looking for duplicate first components here, right? Duplicate input value. So the idea here is that I input a value for the takeoff city, and I should get an output as the destination city. So I have New York, Boise, Baton Rouge, and Denver. None of those are repeated, right? So this guy's going to be a function. We can see it more clearly with this mapping diagram. Again, the X are the domain. Those are the takeoff cities. The Y are the range. That's going to be the destination cities. A flight from New York is associated with the destination of Miami. A flight from Boise is associated with a destination of San Diego. A flight from Baton Rouge is associated with a destination of Orlando. And a flight from Denver is associated with a destination of Dallas. So each X or member of the domain, each takeoff city, is associated with one and only one Y or member of the range or destination city. So we can say this is a function. Let's look at one more problem, and then we'll kind of move on. Again, in the next lesson, we'll start looking at things that are much more complicated. So for G here, again, we're going to have the same thing, takeoff cities and destination cities. So it's equal to, we have this set with Portland, Chicago, Seattle, Houston, Los Angeles, Pensacola, and Los Angeles, Little Rock. So immediately you see the first component here and here, those are the same. So this violates the definition of a function, right? I'm taking off from Los Angeles and there's no clear association between my destination city. Am I going to Pensacola? Am I going to Little Rock? You can see this more clearly in the diagram where we show the mapping, again, from X, the domain, the takeoff cities, to Y, the range, the destination cities. So a flight from Portland lands in Chicago, a flight from Seattle lands in Houston, a flight from Los Angeles lands in Pensacola and Little Rock, okay? So that's where you get the problem. This X value, this member of the domain, Los Angeles, is associated with Pensacola and also Little Rock. So if I take off from Los Angeles, I don't know where I'm going to land. Am I landing in Pensacola? Am I landing in Little Rock? That might be a problem if I'm trying to book a hotel or have somebody pick me up. So this guy is not a function.